So hello everyone. Today I'll be presenting this article that was published last year, which is called Qualifying Quantum Approaches for Hard Industrial Optimization Problems. And it's looking at data which comes from electric vehicles and charging stations. So we're trying to have some really hands-on using some quantum algorithms. This work was done in collaboration between EDF and Pascal, the company where I work when I'm doing my PhD. Pascal is a company which is building quantum processing units based on neutral atoms, and today I'm going to show you a bit the kind of optimization tasks that we can do on such type of computers. So I just want to come back a bit on the relationship between that computer scientists have with quantum mechanics and then what physicists have as a relation to quantum mechanics, and show a bit how both of them are going to converge and how we can write some optimization problems which use a bit of physics inside of it. So Benioff in 1982 introduced the idea of a quantum Turing machine. So this idea is that I'm given a Turing machine, but with the internal states, which are replaced by states of a Hilbert space, and also the transition function is replaced by a collection of unitary matrices. So the idea behind this is to say, if I'm given a Turing machine which is guided by quantum mechanics, what can I do with it? And in 1997, Bernstein and Vasiliani came up with the bounded error quantum polynomial time class, BQP. And it said that in the language L is in BQP, if and only if there exists a polynomial quantum Turing machine, Q, such that if a word X is in L, then the probability that the polynomial QTM given X returns 1 is superior or equal to 2/3. And at the same time, if the word is not in the language, then the probability of Q of X equals 0 is superior or equal to 2/3. And so computer scientists afterwards have been wondering, where does this BQP class, so basically all the quantum computers, where do they sit inside of the complexity landscape in the complexity landscape of classical computer science? And so we started obviously with the class P, which is polynomial time. Then we add the class NP, which is non-deterministic polynomial time. Over this, inside of this, we have the NP complete part, which is the intersection between NP hard problems and NP problems. And then we have, bigger than this, we have the polynomial hierarchy, which is kind of a tower of NP oracles. And all of this is going to sit inside of P space, which is the polynomial types of problem which are can be represented in polynomial space, but can maybe take exponential time to find a solution. And so the question is, where does BQP sit inside of this, and can we expect some speed up from quantum machines versus classical machines? And so what we discovered is that obviously we think today that BQP has this kind of shape inside of the complexity landscape. And of course the algorithm of Peter Shor factorization in 1996 shows that BQP holds some part of NP. And then there was an oracle separation of BQP and PH done by Raz and Tan in 2018. So there is some, this is why there's been a lot of aura behind quantum computing, because we believe that it can make some problems which are hard for classical computers easier for quantum computers. Now if we look on the other side of the spectrum, we look at physicists who look at quantum mechanics. This has been developed at the beginning of the 20th century. And so all of these physicists have been studying many different kind of phenomena, such as wave-particle duality, black body radiation, photoelectric effects, etc. And in this case, what they discovered is that the evolution of such quantum systems is governed by what is called the Schrodinger Equation. And this Schrodinger Equation is just a differential equation in which the system is represented by a state vector psi. This psi, if my system is composed of n, for example, let's say n atoms of two-level atoms, then the space which encodes all the information about my state vector is a complex vector of size 2 to the power of n. So you need an exponentially big vector to describe a quantum system. And then the evolution is guided by what is called the Hamiltonian, and this is going to be very important because it's the resource we use in our computers to find the solution to optimization problems. And so this Hamiltonian is a matrix, so it's also of size, it's 2 to the n times 2 to the n matrix. So it's usually very big. And so when physicists are trying to understand phenomena of physics, such as superfluidity or superconductivity at room temperature, what they have usually is that they have candidate Hamiltonians, and they're trying to solve this equation. The problem is, because the state grows exponentially big, when you arrive at a number of atoms which is superior to 40, then the dynamics become classically intractable. And this is why physicists have been trying to create some simulators of quantum mechanics using cold atoms. So you see that there's this idea that the quantum state has an exponential amount, it requires an exponential amount of information to describe. And so people have been thinking that maybe we can encode problems which are exponentially big inside of quantum systems and then try to find a solution. And so this is what I'm going to show now, is how we're going to exploit the exponential Hilbert space and use the Reedberg dynamics, which are dynamics used by the cold atoms that we're using at Pascal, and how we can encode a very common problem of optimization. So we're going to look at the following task, which is finding the maximum independent set of a graph with V the vertices and E the edges, and we suppose that we have a number of vertices which is equal to big N. So mathematically, it's just that we're trying to find a subset S of the vertex set, such that for every two nodes which are part of this subset S, there exist no edges that's between those two nodes, X and Y. So just as an example here, you see the Peterson graph. So the blue nodes are part of the MIS, as no two blue nodes are connected together. And we're trying to find this maximal, this ensemble S, which is maximal. And in this case, it's the case. If you want to add another node, a black node into blue, then you will have two nodes blue which are connected. So finding this is known to be NP complete on graphs, but also on different, like on planar graphs and unit disk graphs. But what's interesting is that because every node can be either blue or black, it means that each node can be in two different states. So when I look at a solution, it's going to be a specific coloring of my graph. And it's either going to be 0, it's going to be just a bit string of size n with 0 and 1s, 1s being the blue and 0 being the black. So the idea is that my whole space of solutions is exponential. It's 2 to the power of n. And so now what's great is that you can think, okay, but I can in fact encode all of the solution, the space solution, inside of a system with n atoms. So this is what we're going to do. And this is how it works at Pascal. So we have an atom. So the atom has energy levels. The first one is called the ground state. It's the one that's in which the atom is naturally. And then we have an excited state, which is much higher in energy, which is called the Reedberg state. In this Reedberg state, the electron is 1,000 times further away from the nucleus than what it should be normally. And so these are two states that we call ground and Reedberg, from which you can switch using a controlled laser field inside of the lab. And so now if I have my n atoms, then I can just encode all of the state space solutions for my MIS problem inside of n atoms in such a way. But it's not sufficient that I just encoded the problem inside of the system of atoms. I also need to find the solution, right? And so now I have to write an algorithm, find a way of finding this good solution. And so what we're going to use is what is called the Reedberg blockade radius, which is quite natural in atoms. So the idea is that if I have two atoms which are, so here's the distance axis. If I have two atoms which are separated of a distance r, if it's inferior to a distance rb, which I call the blockade radius, then you see that I can have two atoms in ground state. But if I want to excite both atoms at the same time, there's this energy shift of the doubly excited Reedberg state, which means that basically two atoms which are close cannot be excited to the Reedberg state at the same time. So you create a condition where two neighbor atoms cannot be excited at the same time. And so we're going to use this dynamic to encode the MIS problem by saying that quite naturally what we're going to do is use these dynamics, and we know that by the end, because two atoms cannot be excited to the same Reedberg state, we're going to try to maximize the number of atoms in the Reedberg state, and this is actually going to be, we can show that it's the solution to the MIS problem. And so here is just a graph showing that this is the Reedberg blockade radius, so it means that the central atom in red is controlling all the other atoms in gray, meaning that all the atoms in gray cannot be excited to the Reedberg state at the same time as the red one. So this is work that has been done at the Institut d'Optique in Paris-Saclay. And just to show you a bit the dynamics, this is the kind of, when I was talking about the Hamiltonian, which gives you the dynamics of the system, the kind of Hamiltonian that you can engineer is called the Quantumizing Hamiltonian. And so if you're familiar with quantum mechanics, These are Pauli matrices, sigma x, sigma z, and this is also this is the interaction term between Reedberg atoms. But what you really have to keep in mind is just that this is the dynamics. What I was showing is basically you're trying to excite a maximum of atoms, but two atoms, neighbors, cannot be excited at the same time. And this is basically what's happening in my dynamics. And what's interesting is that, in fact, so in the lab, the omega, the delta, and the distance between the atoms can be controlled by the experimentalist. So this means that we can engineer Hamiltonians to represent either the cost function for MIS or a lot of different stuff. And so the scheme is the following. I take atoms, and I can, in fact, put them in space. So each black point is going to represent an atom. I'm going to put them in such a way that two atoms which are inside of each other's Reedberg blockade sphere are connected. So at the end, what I get is the graph on the right. And then I can use the Hamiltonian I showed you before, changing the parameters, taking omega equal to 0. I can encode this cost Hamiltonian, which basically says I'm going to try to minimize this cost function. And this is going to say this is equal to 1 if my atom is excited. So the more atoms are excited, this is positive, so this is going to be very negative. So I want to have a maximum of atoms which are excited, but at the same time I have a huge penalty cost, which says if both are excited at the same time, then I add a massive positive number. And so the solution to this is indeed the maximum independent state. And then I'm going to use what's called, so now I can encode the solution in my Hamiltonian, but now to find it, to get the system to work towards the solution, I'm going to use something which is called the QAOA, with a mixing Hamiltonian, which is going to propagate the state from an initial state to the rest. And it's this method which has been described in many different literatures and by Fari in 2014. And the idea is that it's a variational quantum circuit which enables to prepare a specific state. And this is what we do. I maybe not go through the details, but basically we can construct at the end the solution. And so now what you see here is results that we have from simulations. So we took 84 instances. These instances of maximum independent set were built from a data set which comes from electric vehicles from Paris, from charging stations. And what you see on the x-axis is the depth of a quantum circuit. So it's the depth of this. So here I'm showing I can put many different layers. I can apply my mixing Hamiltonian, my cost Hamiltonian, different layers at a time. And so the more layers I add, the closest I will get to the exact solution. And so what you see on this graph is that at the approximation ratio counts is between 0 and 1. If it's equal to 1, it means that I found the exact solution. And it's determined as the size of the set that is returned by my quantum computer divided by the true MIS size. So in this case, we know the size of the true MIS. We're just checking if we're finding it or not. And so you start at layer 1, and you see that you have quite decent approximation results. And then as you have a bigger and bigger depth, what you get is that the approximation really rises, but maybe for what we realized is that for some classes, so the green graph, it goes very well, it just keeps increasing, but the orange graph doesn't seems to be stationary. So we suppose that we have achieved a local minima, which we didn't get out of from layer 2 to layer 7, but this has been ongoing work of investigation. Yes, and of course, experimentally, if you try to do this experiment, because the quantum computer is noisy, these simulations were done with a perfect quantum computer, but because it's noisy, the more depth you have, the more noise accumulates, and so the less effective your dynamics are. So what you're going to see is, in fact, you're going to get a kind of a bump at 2 or 3 layers, and then it's going to go back down, because there's so much noise that you just can't control the parameterization that you're doing. As in conclusion for future plans, what we realized, talking with the people from EDF, from operational research, is that they told us, fine, this problem is interesting, but do you know that solving MIS on a unit disk graph is actually has an approximation scheme which is extremely powerful. And so we realized that, so this is the class of complexity of approximations of NP problems. And we realized that a lot of problems, in fact, can have some very good approximation schemes. So you can find a decent solution in polynomial time. And so our problem sits here in this PTAS. It's the maximum, not planar, but unit disk, but it has the same complexity. And so what we've shown in this article is that at least quantum approaches are on par with classical approaches in this case. We can also find approximate solutions of the same type of quality. But what's inside of the red is really the optimistic classes, the ones you can do quite easily with a classical computer. And so now the big question is, where does this if green represents my quantum computer, where does it really sit? Am I capable of probing some dynamics outside of the optimistic classes? And if it's the case, this would be quite remarkable, because this would really show a massive practical quantum advantage. But this, of course, has been ongoing work. There are a lot of different things that we've been studying. And yeah, that's it. Thank you for your attention. And if you have questions or anything, there's my email address. So please feel free to send a mail if you're interested. Thank you very much.
Any questions?
Yes.
Vas-y.
Bonjour, merci beaucoup pour cette présentation. Je me lance avec la question de débutant. N'hésitez pas à me dire si c'est trop simpliste et qu'on doit discuter ça dehors et ça risque de prendre beaucoup de temps. J'ai étudié l'informatique très classique avec les transistors, les flip-flops, etc. pour le codage des informations.
Ouais.
Et j'ai beaucoup de mal à comprendre l'analogie. Si vous pouvez, d'une manière très simple, nous montrer ou expliquer le lien ou l'analogie entre les deux systèmes de calcul.
En 2 minutes.
En 2 minutes, promis.
Sinon, on se voit tout à l'heure à la pause café.
Oui, bien sûr. Bah, je peux vous expliquer vraiment en 2 minutes. Donc l'idée, c'est que l'information, elle est encodée de la même façon. Ça reste des 0 et des 1. C'est juste que la façon dont cette information est encodée et va évoluer est différente, parce qu'elle est régie par les lois de la physique quantique et pas par les lois de la physique classique. Mais donc vous voyez que là, mon atome a 2 niveaux, donc le ground et le Reedberg. Ce sont 2 niveaux qui vont représenter mon 0 et mon 1. Et d'ailleurs, quand j'essaie de résoudre ce problème de graphe, je suis en train de regarder quelque chose qui est je regarde des solutions qui sont en fait des bit strings. Donc j'ai effectivement il y a un encodage de mon information avec du binaire. Ouais.
Donc au niveau, l'encodage ne se fait pas avec des flip-flops et des transistors, etc. Mais c'est au niveau de l'atome, c'est ça?
C'est ça, c'est au niveau de l'atome. Donc on utilise des lasers qui permettent de passer d'un niveau électronique à un autre.
Ça, c'est pour enregistrer l'information?
C'est ça. C'est ça, c'est pour mettre de l'information sur l'atome. Et ensuite, on le fait évoluer avec un... donc c'est là, alors nous, notre approche, on appelle ça analogique et pas digitale, c'est-à-dire qu'on n'applique pas des portes logiques comme en informatique classique, mais on vient modifier ce hamiltonien-là, qui varie dans le temps de façon continue. Et en fait, on s'est rendu compte que ça peut être assez puissant pour déterminer des solutions à des problèmes. Donc ça, c'est aussi une différence, c'est qu'on ne fait pas du digital, on fait de l'encodage analogique.
Merci.
Très bien, 2 minutes. D'autres questions?
Je me demandais, comme vous modélisez votre graphe avec des atomes qui sont à une certaine distance,
oui.
Est-ce que ça ne limite pas fortement les graphes qu'on peut modéliser comme ça? Et est-ce que c'est pas même compliqué de modéliser le graphe qu'on veut?
Exactement, c'est exactement ça. Donc effectivement, la classe de graphes auquel on est limité avec des atomes dans ces conditions-là, ce sont des graphes qui sont unit disk, donc avec des rayons finis. Et donc comme ce sont des graphes qui ont une contrainte géométrique, en général tous les problèmes qui s'appliquent, les problèmes qu'on a dessus, de trouver la mi-s, une coloration et tout, en fait, il existe toujours des heuristiques qui exploitent la géométrie du graphe. Et donc on a des solutions beaucoup plus simples que dans les cas de pire complexité. Donc je suis d'accord, c'est très limité, mais on travaille en ce moment sur une façon de généraliser à des graphes plus difficiles, mais c'est un travail qui n'est pas encore fini. Mais c'est évidemment une des directions importantes dans lesquelles on est.
Et du coup, il faut la construire en hardware
Oui.
Le
Alors, oui, exactement. Donc nous, on a des... J'ai quand même vous montrer une...
Je sais pas, on a des résultats théoriques sur les unit disk graphes par rapport aux graphes généraux. Est-ce que quelqu'un sait ça?
Alors on sait que c'est NP complet dans le cas exact, mais que dans le cas d'approximation, c'est beaucoup plus. Il existe des schémas d'approximation en temps polynomial qui sont excellents.
C'est une classe de graphe qui est utile pour...
Ouais. J'aimerais juste vous trouver parce que je n'ai pas de mise, mais Voilà. Je vais juste vous montrer à quoi ça ressemble en fait dans la vraie vie. Ça, ici, là, ce que vous avez là, c'est une photo en fluorescence dans la machine. Ce sont vraiment les atomes qui ont été placés individuellement à l'aide de pièges optiques. Donc on est capable de faire des formes en 1D, 2D, mais aussi en 3D. Et donc on a même réussi à faire une tour Eiffel, mais qui fait des millionièmes de centimètres, composée d'une cinquantaine d'atomes. Donc c'est vraiment... les graphes sont représentés tels quels, avec des atomes individuels dans la machine.
Et du coup, c'est reprogrammable facilement.
Exactement. Ouais, vous pouvez faire n'importe quoi comme forme, c'est juste que les interactions qui vont avoir lieu, elles, sont régies localement par les contraintes d'atomes proches.
Ok. Une dernière question, parce qu'après...
Au niveau du bruitage par rapport au nombre de layers calculés, est-ce qu'il y a des potentiels d'amélioration?
Oui,
je suppose qu'il y en a, mais je veux dire, quelle est la perspective là, sur les prochaines années à ce niveau-là?
Donc, ce qu'on a montré là, ici, donc l'utilisation du QAOA, c'est pas la même présentation, celle que je vous ai, celle-là, donc ça là, donc cette idée du QAOA, de faire des couches, en fait c'est un modèle c'est un modèle théorique, mais on s'est rendu compte que chez nous, c'était peut-être pas la peine de faire ce genre de modèle QAOA, et nous ce qu'on fait c'est autre chose, on fait on fait un processus adiabatique où on part d'un Hamiltonien qu'on connaît, on a un état de plus basse énergie qui est connu, et on va doucement faire converger le système vers un autre Hamiltonien, et en fait on sait que l'état dans lequel est l'ensemble d'atomes va converger vers l'état de plus basse énergie. Et ça, on a beaucoup moins de bruit là-dessus que sur ce genre de procédure. Sur ce genre de procédure, le bruit est de l'ordre sur la solution optimale, en gros, on a une perte de 5 à 10% de qualité.
Merci. Il y aura 2 présentations sur la diabatique tout à l'heure. Merci bien.
Merci.